Chapter 5 Chemistry of Actinide. Actinide constitute a series of elements following actinium in the seventh period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanoid in the previous chapter. Lanthanoid which follow lanthanum involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called actinides. Actinide along the lanthanoid constitute complete F block element. The ending ID in actinide is not appropriate because it is more correctly means negative ion, such as oxide or chloride. Actinide were also named actinone by a group of scientists. However, the ending on is used preferably for non-metal, whereas all the actinide are distinctly metallic. IUPAC have now recommended these elements to be called actinoids with the ending OID rather than being called actinide or actinones. However, it is unfortunate that people still call these elements by their earlier name as actinide. Before World War II, only naturally occurring actinide, namely thorium, protactinium and uranium were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reaction. These elements are named man-made or synthetic element. Another name coined for these elements is transuranic element. Transuranic element are the elements that have atomic number greater than 92. Position of actinoid in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as 6s2, 4f14, 5d10, 6p6. After radon, the 7s and 7p orbital gain stability relative to 5p orbital because s and p orbital are more penetrating than the d and f orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new element, francium and radium, belonging to s block of element. After the addition of two electrons in the radon core, the 5f and 6d electron penetrate the 7s orbital. The least penetrating f orbital are stabilized on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium to lawrencium enter the 5f shell. It is important to note that around actinium, both the 5f and 6d subshell possess almost similar energies. Because of similar energies of 5f and 6d subshell, the incoming electron may enter either of the two subshell, which result in the uncertainty of the electronic configuration. As a result, it is doubtful whether the electron enter the 5f orbital or not. However, once filling start in f orbital, the 5f subshell become more and more stable. As a result, from uranium onward, the 5f shell become most stable. Thus, all the incoming electrons start filling progressively in f orbital. The general electronic configuration of actinium can be. General characteristics of actinide. Electronic configuration. As already discussed, the actinide involves the gradual filling of 5f subshell. The electron configuration of the title actinium is 6d17s2. Thus, from thorium onward, the 5f subshells start progressively filled. The general electronic configuration of the atom of the actinide in the ground state may be written as 5f1214, 6d0217s2. Physical properties. Melting and boiling point. The melting and boiling point of actinide are moderately high but are lower than those of transition element. Density. An inspection of the table 5.2 reveal that the element near uranium have very high density. Americium resembles the corresponding lanthanide europium in being less dense than the neighbor. Atomic and radii in actinide contraction. The ion of the actinide, the size of the actinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the f electron. This steady decrease in ionic radii with the increase in atomic number is called actinoid contraction. A comparison of M3 positive ionic radii of actinoid with those of lanthanoid reveals that the actinide and lanthanoid ion are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ion in case of actinide is shown. It is interesting to note that there is a great decrease in the atomic radii from thorium to uranium, which may be due to increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from thorium to uranium may be considered to consist of M3 positive ion with a total of any electron per atom. After plutonium, the metallic radii increases significantly again, which may be reflect the increase in lanthanoid like behavior of the inner later actinoid, in which the preference oxidation state is +3 with only 3 electrons available for metallic bonding. Oxidation state. The actinoid elements show a greater range of oxidation state than the lanthanoid. The different oxidation state of lanthanoid element are shown. The +2 oxidation state in case of actinoid is very rare. Am2 positive has the electronic configuration analog of Eu2 positive in the lanthanoid, but exists only in the solid state as the fluoride AmF4. On the other hand, exists as ion in solution. The properties of divalent actinoid resemble closely to Ba2 positive in group 2. The most stable +2 oxidation state is exhibited by nodinium, corresponding to stable 5F14 arrangement. The +3 oxidation state is the most common state among all the actinoid. However, the +3 always the most stable oxidation state in the actinoid. The first 4 element show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized. The solution. Interestingly, the most stable oxidation state of element up to uranium is the one involving the valence electron. The most stable oxidation state of PH, P and U are +4, +5 and +6. Although neptunium show the oxidation state +7 by involving all its valence electron. The most stable state. This is the NPN +7 oxidation state is highly oxidizing and the most stable. The +4 oxidation state is exhibited by all the elements from thorium to Cf. However, NP display the most important +4 oxidation state. The M4 positive ion are known in the acid solution. The element all form dioxide MO2 and fluoride MF4. The +5 oxidation state is exhibited by all the elements from Pa to Ma. However, oxidation state is the most stable for Pa and Mp. The +6 oxidation state is exhibited by lower actinoid in the form of fluoride. The oxidation state is more commonly found as a dioxo ion. The ion of the linear end exists both in the solid as well as in solution. One of the most commonly encountered compound of uranium is +6 oxidation state is uranium dihydride. It consists of linear DuO2 2 positive ions surrounded by the NO3 negative ion. Color of the ion. Actinide ion are mostly colored. The color of a particular actinide ion depends upon the number of electron present in the 5f orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cation formed by actinide ion in aqueous solution. In addition to FF transition in actinoid, the color can also be arise due to FD transition as well as charge transfer electron. The color of actinide ion solution because of FF transition occur in the visible and ultraviolet region. We have already encountered this FF type of transition in case of lanthanoid as well, since the 5f electron in case of actinide are projected out more in space than the 4f electron in lanthanoid. These 5f electrons are most strongly influenced by the ligand field of ligand. This makes the absorption spectra of actinide more complex compared to the straightforward spectra of lanthanoid. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transition in case of actinide are nearly 10 times stronger and 2 times broader than the FF transition of lanthanide ion. The energy difference between 5f and 6d orbital in case of actinide being smaller than 4d and 5d orbital in case of lanthanoid. The actinide ion invariably absorb light of lower frequency. As a result, the allowed and very strong FD transition lie in the ultraviolet region and therefore do not influence the color of the actinide ion. It has been observed that actinide ion in higher oxidation state display predominantly charged transfer spectra. This spectra is exhibited only by high oxidation state ion which can easily oxidize the ligand. It is important to note that lanthanoid do not exhibit color charge transfer spectra because lanthanoid do not display oxidation state higher than 4. Magnetic property. The actinide shows similar magnetic properties to lanthanoid in terms of magnetic moment with the number of unpaired electrons. It is important to note that high valence state have been chosen for 5f1, 5f2, 5f3 and 5f4 ion which show the close similarities. Magnetic moment value of the isoelectronic actinide ion are lower than the lanthanoid ion. This is due to the fact that 5f electron actinoid are projected more out in space to the crystal field. Reactivity. The actinide are highly reactive metal. These react with dihydrogen and form non-stoichiometric hydride with the formula Mh2. They react with hot water. Actinide react readily with HCl, but reaction with other acid is slower than expected. The metal are basic and do not react with sodium hydroxide. Thorium and uranium chemistry has been explored in detail. Occurrence and isolation of actinoid. All the elements beyond actinide in the periodic table are radioactive. As a result, the nuclei of all the actinide are unstable and undergo radioactive decay. Among the actinoid, uranium is the heaviest naturally occurring element with an abundance of 2.4 ppm in the earth crust. Uranium. Since uranium is the most important of all the actinide, its chemistry will be discussed in more detail. The primary natural source of uranium is pitch blende or uraninite, which is the empirical formula U3O8. It is a mixed oxide containing uranium both in 4 and 6 oxidation state. Extraction of uranium. As already mentioned, the main source of uranium is pitch blende. The detail of extraction of uranium involve the following step. Concentration. The ore is crushed to a fine powder and is subjected to a conventional gravity separation to remove the lighter impurity. Roasting. The concentrated ore is roasted on the earth of a reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic and antimony. Acid treatment. The roasted ore is treated with dilute H2SO4 in the presence of an oxidizing agent such as MnO2 and NaClO3. This treatment converts uranium to a soluble uranyl sulfate. The roasted ore can be converted to a solution of UO2NO3 twice by dissolving the ore in nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uranyl sulfate precipitates it as ammonium uranyl carbonate. Conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating, either with charcoal or hydrogen. Production of uranium. Elemental uranium can be produced from uranium dioxide by using either of the two methods. UO2 is heated with vapor of HF to form uranium fluoride, which in turn reacts with magnesium to yield uranium metal. Isotope of plutonium can be prepared by reaction in which a fast neutron is added with the subsequent loss of 2 neutrons. The yield of heavy element is controlled by two factors: the half-life of various isotopes by their ability to absorb neutron. The separation of these elements from uranium is extremely difficult. It is because these elements, including the static material, are not only highly radioactive but also give highly radioactive fusion product. So the separation of NPPU and AM from uranium are based on the following chemistry. Stability of oxidation state. A steady decrease in the stability of high oxidation state with the increase in atomic number have been observed with the increase in atomic number. The order of stabilities of the major ion involved are: separation of these elements from uranium from fission product and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. Extraction into organic solvent. The MO2O2 positive ion from solution can be extracted into organic solvent. The M4 positive ion are extracted into tributyl phosphate in kerosene. Ion exchange method. Ion exchange method are commonly used in separation for small amount of material, as in separation of americium AM spent uranium fuel rod removed from the nuclear reactor can be used to extract NP and PU in kilogram quantities, whereas AM in 100 gram quantities. This reprocessing of nuclear fuel rod is an important technology, as this helps to extract new element that may be used as nuclear fuel. Spent fuel rods are dipped in pond of water for several days to allow them to cool. During this dipping period, the intensity radioactive isotope with short-lived lives lose most of their activity. The fuel rods are dissolved in 7-MHNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficient of the actinide in 7-NHNO3 solution containing 30% tributyl phosphate in kerosene are. As a result, nitrate of UO2 positive and PU4 positive are preferably extracted in tributyl phosphate, leaving the other actinide, namely NP and AM, along with other fusion product in aqueous solution. This PU4 positive is reduced to PU3 positive, which enter the aqueous phase, while UO2 positive remain unchanged in organic layer. UO2 positive species present in kerosene oil on treatment with 0.2 NHNO3 give UO2 in aqueous solution. On the other hand, aqueous solution of reduced PU solution on treatment with nitrous acid get oxidized to PU4. This solution reacts with oxalic acid to give crystalline precipitate of the composition. The separation of other actinide, namely NP and AM, can be achieved by the use of appropriate oxidation reduction cycle coupled with solvent extraction. For example, PU3 positive and aqueous nitric acid can be oxidized to PuO2 positive by an oxidizing coupled with the later or heavy actinoid element. The element from curium onward, namely curium, berkelium, californium, istinium, permium, mendeleum, nobelium, lawrencium are named as later actinoid. Very little is known about the chemistry of these elements actinoid because of their limited availability and extreme instability. It is clear from the table that curium is available only in macroscopic quantities, whereas the later actinoid, above atomic number 100, have been prepared only in minute quantities. Comparison of actinoid and lanthanoid. Both actinoid and lanthanoid constitute element of F block, as these involve the gradual filling of 4f orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Point of similarities. Both the lanthanoid and actinoid involve the filling of f orbital. Both the lanthanoid and actinoid display predominantly the +3 oxidation state in most of their compound. Due to poor shielding of 4f and 5f electron, both show gradual contraction in the size of their atom with an increase in atomic number shows the lanthanoid and actinoid contraction. Element of both with the same number of unpaired electrons display similar absorption spectra due to FF transition. Both are highly electropositive and are very reactive. Nitrate, sulfate and perchlorate of trivalent lanthanoid and actinoid are insoluble in water. Hydroxide, fluoride and carbonate of trivalent lanthanoid and actinoid are insoluble in water. Both actinoid and lanthanoid can be separated by ion exchange method. Thank you.